The next set of problems that I will be looking at involve flames that are multidimensional. But before we do that, I want again to focus on the planar flame and to just take another look at what we have obtained. And so here is the structure of a planar flame, right? The temperature rises to the adiabatic temperature. The concentration of the fuel is consumed and then goes to zero. When it's all consumed, the reaction rate takes a fractional region of the entire flame thickness. And the flame thickness is measured here as LF, which is where the temperature is almost the cold temperature to the region where it reached almost the adiabatic temperature. Now, if we look at this structure on a much larger scale, or think about it if you go further away from where your flame is, and the larger scale is what I called capital L, which is something maybe of the order of your combustor or what I would call some hydrodynamic length, then this entire flame will look like a very sharp discontinuity in a thin region compared to this large L, right? And the temperature will be almost discontinuous. In other words, will go from cold to hot, right? From TU to TA, and there will be a discontinuity in Y from the given value to zero. And the entire flame, the entire means the preheat and the reaction zone, is a very thin region. In reality, it's like a fraction of a millimeter. So if my length, hydrodynamic length, is something like a few centimeters, then it's very thin, it's very narrow compared to the capital L. And so we can view the flame as the entire flame, remember? That's why I was a bit careful before when I use inconsistently the flame thickness or flame location, and I really meant the reaction zone location. Okay, so now it's the whole flame can be viewed as a discontinuity in this case, and but the discontinuity is going to be discontinuity in temperature, in density, and in concentration. For example, if you look at a Bunsen flame, you see that the flame region is this very thin dark blue region compared to something which is relatively much larger, which is the size of the Bunsen burner. And so what we would like to be able is to describe multidimensional flames in this limit, in the limit where the flame thickness LF divided by capital L, which I call delta, is very small or goes to zero. In that limit, the flame, which is described here as the red region, inside which that's the structure that you have, right? This whole flame can be viewed as a surface, and mathematically I can describe it by some function of position and time equal to zero, right? That's a surface in the space. Or explicitly, I can write it as x equal to f of y zt. In other words, if I can take that function and explicitly write it as x equal to a function. So those two descriptions are equivalent. This is a more implicit form, and this is an explicit form, and I will be using them. I will be using both of them depending on the case I want. So now the flame is therefore a surface that separates the unburned gas, which I will, for convention, I will use that F is negative in the unburned region and F is positive in the burned region. I have to set up my convention properly, and then a unit normal to the flame surface pointing toward the burned gas will always be considered positive in my notation. So in some places, people choose the unit normal towards the unburned gas. So it's a matter of convention. So this is important. Okay. So now here is in the limit. So this is what I just said. Now the unit normal. Well, before I go here, then this flame is propagating into the unburned mixture or into the fresh mixture. at some velocity Vf. Vf is the absolute velocity that the interface is moving, okay? It's not what we call the flame speed. I will define flame speed in a minute. Okay, so these two quantities, Vf and n, are simply geometric quantities. Given a certain surface, you can determine them. And here they are determined. The normal is determined as the gradient of the function f divided by its norm so that it becomes a unit vector, or in this explicit description, it's written like that. The velocity of the interface, and usually it's the velocity in the normal direction, and so the normal velocity of the interface, because the flame basically propagates normal to itself, is minus this capital F sub t, which means the partial derivative with respect to t, and divide by the gradient, or in this form. So for example, if the flame was planar, the absolute velocity is just the position the derivative of F sub t. Those are 1. And the normal is going to be just 1, which is the direction, say the axial direction that it propagates. Okay? So this is just geometric quantities. Now, what we call the flame speed is the propagation speed relative to the incoming gas. So if the incoming gas is at rest, then the flame speed is Vf. If the incoming gas is moving at some speed and the flame is stationary, then in fact the flame speed is exactly the velocity of the gas normal to the surface. So here is the definition. That's nothing more than a definition. It's the velocity of the interface, the negative because we called positive in the direction of the burn gas. So it's the velocity of the gas, of the interface relative to the gas. Okay, now in this hydrodynamic description, then what you see, in other words, when delta is very small or delta goes to 0, what you see is that the governing equation, in the governing equation, all the diffusion terms turn out to be of order delta. Okay, they are small because diffusion in a small region is essentially negligible, and so one obtained just the Euler equation, okay, which are written here, okay. In addition, the Euler equation here, and I have included gravity as well for now. At some point we will need it, so I left it in. Now the equation for the temperature and mass fraction just reduced to these, which essentially says that the material derivative is 0, which means that if you start in a mixture which is uniform, every fluid particle have the same temperature as the other. dt by dt is the time rate of change of the temperature of the fluid particle, but they all have the same temperature, so nothing is going to change up to the flame. Now, what happened behind the flame? Well, behind the flame, the assumption is that, so this is what I wrote here, T equal to Tu. What happened behind the flame? The assumption is that the flame temperature along that surface, in other words, the flame is going to be some kind of isotherm where the flame temperature is constant along it, which is not precisely true, and we are going to revisit that later. But that's, at least for now, an assumption. And so if the flame temperature is the same along the whole surface, then every fluid particle will be transporting that same temperature behind, and so the temperature behind is also going to be Ta. Of course, there is no heat loss in this description. And so the temperature is a piecewise constant function, Tu and Tb. As a result, the density is rho u, rho b, and the mass fraction is going to be Yu and 0. Okay? Now, clearly, Tb has to be the adiabatic temperature, and so what we have denoted here is that the density ratio, which is equal to the ratio of the burned to the unburned temperature, I denoted it by sigma. Sigma is always bigger than 1, right? And I refer to it as a thermal expansion parameter. And typically, sigma is about 5, 6, 7 in that range. Okay. Now, and as I said, I'm going to assume clearly that the burn temperature is adiabatic temperature, so it's given by this expression. Okay? Now, it turned out that this model, which, well, let me finish it, and then I will make that comment, which is here at the bottom. And so here is the model, the entire hydrodynamic model so far. So we have seen that the equations reduce to Euler equation, and because the density is piecewise constant, then the continuity equation on one side or on another satisfy the incompressible equation. But of course with different density. In other words, in the momentum equation, there's a rho u on this side, a rho b on that side. So the entire problem is not incompressible. The entire problem is a variable density flow, okay, except that the variation occurs very sharply at the interface. Okay, so these are the governing equations, have to be satisfied on one side or on another. These equations, by the way, are not valid across or are not valid in the thin red region that I'm describing as an interface being the flame. Now, since these are the Euler equation, the condition across the flame must be the Rankine-Hugoniot relation that we have derived early on in the first day. And those are the Rankine-Hugoniot relation. Essentially, it tells you that the mass flux in is the mass flux out, that there is that the tangential velocity is continuous, and that the momentum in the normal direction is conserved. Finally, these two boxes are not sufficient to solve the problem, because we have equations on one side or another of the flame, but we don't know where the flame is. And so clearly we need one more condition. And that one more condition is an equation for the flame speed. Now, I have defined a minute ago the flame speed being the velocity of the interface relative to the flow. And so the assumption is, it's a hypothesis at the moment, that the flame speed is constant and it therefore must be equal to the laminar flame speed. Now, later in the lecture, I'm going to modify this hypothesis, okay? Now, I am using this first because it will be easy to gain some understanding of some problems that I want to do, and later we will see variation of that. Now, as I just said a minute ago, I skipped that sentence here. This model, including the flame speed that I just said, was confirmed as being the leading order term solution in asymptotic limit in which delta goes to 0. So it's not made up, and the fact that I use here hypothesis has been verified, but this is essentially was first suggested by Landau and Dario in their famous analysis of hydrodynamic instability of premix flame, which we will discuss later. And so I have used that model to begin with the discussion. Okay, so the first thing that we do when we have a model, we have to test it on some simple problem. And the first problem to test it is on a planar flame, because we already know the solution of a planar flame. But because I forgot that there is one more thing I want to say before I get there. So the one thing I wanted to say is that the flame speed relation, which is written here, right? So flame speed is equal to the laminar flame speed. That's an equation that is equivalent of saying where the flame surface is. Because remember that the normal was the gradient of F divided by F, right? N was the gradient of F divided by the norm, and Vf was minus the partial of F with respect to T divided by the norm of grad F. And so if you substitute that into the relation for the flame speed, right? And you organize the terms, you get this equation here. Okay? It comes from introducing these in here. And that equation is an equation that tells you where is the location of the flame and the shape of the flame. So it's an evolution equation that tells you exactly where the flame is. So if you have, when you solve the problem, is, in other words, solving this problem is solving for the velocity field, satisfying how they move, how they change from one side of the discontinuity to the next, and finding the interface across which these conditions are applied. In some like to call this the G equation, and they use instead of the F the symbol G, but it's the same thing. I will not call it the G equation. I just follow the fact that the first person that wrote that was Markstein, and he used F, and so I will be consistent with that and call it F. I know that people don't like to call the F equation, so maybe the G equation is nicer, but anyway. So the next thing is I rewrote this equation in terms of the little f, which was the explicit form. It's the same thing. Incidentally, the second form shows very clearly that if the flame was planar, so there is no derivative with respect to yz, and if the flame is steady, so ft is 0, then u is the laminar flame speed, right? Or if the flame is moving into a quiescent gas, then u is 0, and these are 0. If it's a planar flame moving in quiescent gas, then these are 0, and then f sub t is minus SL minus because it's moving into the negative direction. Okay? So these are clear statements. The next thing I want to point out that it's not very difficult if you use the fact that the normal velocity relative to the gas is the laminar flame speed. Using this relation for the flame speed, it's not very difficult to see that the Rankine-Hugoniot relation are equivalent to this box, what's in this box here. And let me explain what you have. First of all, note that there is a jump here. But since the jump is 0, then it doesn't matter if I call burn minus unburned or unburned minus burned. But once it's not 0, we have to be consistent. So in my notation and everywhere else, I will be using the jump is going to be burn minus unburned. Okay? You have to be consistent with that. So here it's important, clearly, because there's a non-zero term on the right-hand side. So these relations are equivalent to this, but also be careful. These are general and fundamental. These have used the fact that the laminar flame speed SL is constant. So be careful, don't use that when it's not appropriate, of course. So what it tells you here is that the normal component of the velocity change by a factor proportional to sigma minus 1. So it increased significantly. Okay? The second statement is that the tangential velocity to the flame surface does not change, it's conserved. And the third statement says that the jump in the pressure or across the entire flame, there is a small drop in pressure which is given by this quantity. Now I use the word small. I should be careful because this pressure is already scaled with, remember, the Mach number when we applied the Mach number, the low Mach number approximation. So these are all order 1 quantity. But this P is not the true P. It's this P is just the P that we put in when we wrote that the pressure is equal to capital P plus gamma Mach number square little p. So this is this P. So when I use the word small, I mean that this entire term is small, but not the P itself. P is order 1. Okay. So as I said, the first thing to examine this relation is on simple situation. And the first one is a planar flame. So if we look at a planar flame, which means we have a one-dimensional uniform flow coming at a velocity SL in order to maintain the flame steady and planar, then the gas that is leaving the flame is going to be sigma SL, which satisfy, of course, this relation, right? And since it's planar, then the other relations are irrelevant. And you can write the solution that the velocity ahead of the flame is SL. The gas speed up as it leaves downstream. And you can write an expression for the pressure. And in this case, I have also included gravity. So you see there is an additional hydrostatic term here that changes with position, right, for the pressure. And that term, of course, depends. If it's on the unburned gas, it's rho u. It's on the burned gas, it's rho b. But at the flame, x equal to 0, and of course, the pressure is continuous. Okay? I'm sorry, not continuous, but it has the drop that, that you expect. what I meant really to say is that the hydrostatic effect at the flame is the same, so to speak. It's nothing. Okay, so this is the first case to examine. Now I want to examine this relation a little bit more careful. Okay, so let's look at a slanted flame, and here I rewrote this expression. There is a slanted flame which is stationary. So being stationary, the Vf is 0, and so the laminar flame speed is exactly the normal component of the velocity. So now here is a gas that is coming along the axis. The axial direction is the vertical component, which is the blue. It's coming, and the gas velocity is known. It's some u, let's say, okay? And the question is, how does that change across the flame? And this expression gives you exactly how that happened. So if you decompose the blue vector into a normal component to the surface and a tangential one, the normal, according to this the normal must be, according to this relation, exactly the laminar flame speed. Now, the normal component on the burn side should increase by an amount sigma minus 1 SL. I'm sorry, the jump should be that. So it should increase by sigma SL, which is just much larger than SL, okay? And the tangential component must remain the same. That's the second relation here, right? There is no jump in the tangential component. As a result, the resultant here is this blue curve, blue vector rather. And so what you see is that the flame, as a result of that, is deflected, and the deflection is always towards the normal. Okay, so it deflected always towards the normal. And you can actually determine exactly by how much it was deflected. The rest is simple geometry. If the incoming flow relative to the flame has an angle of theta, then the deflection is given by this expression. And you can verify the limiting cases that they agree and so on. So this is the slanted flame. Now suppose that you have a parallel flow, okay, in the x direction. And if it's a parallel flow, then the only thing, by continuity, the only changes in the flow could be only in the y direction, because the u dx is 0, right? That's the continuity equation. So u may depend on y. So the velocity is u is always in the axial direction of x, but may depend on y. Now, since at the flame, at x equal to f is the flame, the velocity must be the laminar flame speed, the normal velocity. Then if we write what the normal velocity is, it's u divided by that square root. It comes from the expression we wrote before. And if you unfold this relation, you obtain that the f dy is equal to plus or minus 1 over SL, the square root of u square minus SL square. And if you want the position of the flame, you integrate this, you obtain f. Since x equal to f is the flame surface, then x equal to that integral gives you the flame shape, okay? In particular, if u is equal exactly to SL, in other words, if the incoming flow is constant and equal to SL, of course, this is going to be 0, and x is constant tells you that the flame is flat. In other words, incoming gas is exactly the laminar flame speed. The flame that will be supported is a flat flame. Otherwise, it will be slanted. And the question is how to obtain it. So here is, for example, a simple situation of a Bunsen flame where the incoming flow is uniform. So the incoming flow is capital U. According to the previous relation, then the flame position is going to be given by, here is the constant of integration, so it's x minus x naught. It's a square root of u square minus SL square multiplied by y, because when you differentiate this, since u is a constant, then that just gives you a straight line. So the Bunsen flame will be two straight line, which if I set my coordinate, let's say here, then you can write exactly what they are. But in particular, you can determine the angle, right, of the opening angle. and the opening angle clearly will be SL over U because, again, the normal component to the flame surface, as we have seen before, must be equal to the laminar flame speed. And by geometry, you can just obtain immediately the angle theta. Okay? So this is a direct consequence of this relation. Incidentally, well, two comments. First comment, what happened at this apex? Well, clearly the solution that we have been discussing is invalid near the tip or near the apex because remember that we have assumed that the flame is thin compared to its thickness, right? Well, near that tip, the curvature of the flame, usually the flame is curved, and the curvature is quite small, and so it's not large compared to the flame thickness, so the result fail in that region. So we can maybe improve that in that region, but in general, the solution overall is acceptable. Question? Yes.
For a vertical flame, would
a what flame?
For a vertically oriented flame like this,
Yes.
would buoyancy effects affect the flame direction, the gas direction as it goes out of the flame?
It depends on the size, really, of the flame. And when the Bunsen flames are a few centimeters, then they usually will not be affected by gravity. If they are much longer, they may. Yeah. So, I mean, we can obtain the angle, the opening angle. Now, the mathematical solution that I wrote here, in fact, gave us that the flame will be plus or minus. In other words, it's a straight line, and I have composed here two straight lines which form this conical flame, right? Simply by symmetry, I assume that the x, say the position here, I'll take the plus sign for one and the minus sign for the other, or the other way around. But of course, I could have chosen it differently. So for example, I could choose also this configuration. Well, that's certainly the same, and it's acceptable solution, and in fact has been observed in the literature, so in the experimental literature. So it depends really how the flame is stabilized, which one you obtain. If the flame is stabilized on the rim of the burner, which of course this description does not discuss the detail of this stabilization, then the flame will be as such. If it's stabilized by a rod that you put at the center of the burner, then you obtain the so-called V-flame or V-shaped flame, and that's what you have here. But the two are essentially of the same origin, okay? Here are experimental observations that show, maybe I should go back for a second here and say that when U is equal to the laminar flame speed, then you expect the flame to be planar. As the velocity increases, the angle will change and will be smaller and smaller. So it goes from pi over 2 to smaller and smaller angle, right? And so that's really what you see here. As the velocity increases, sorry, the centimeter per second is missing here. This is the incoming velocity at the burner. And this was taken from a book that I forgot right now the name. I should have put the reference there. It's an old book, which is not in print, but anyway. It's a book that discusses mostly experimental techniques and so on. And this is one of the nice figures that I liked, so I put it from there. So you see that the angle changes or the extent of the flame changes as, of course, you increase the velocity. And note, by the way, that the tip, of course, is slightly rounded, as you would expect. But this effect we are going to see in the future that we can understand and explain, perhaps. And the other thing that I want to point out is that when the velocity is sufficiently low that the flame need to be almost flat, it's not quite, right? And at some point, we're going to see that the reason for this is the so-called hydrodynamic instability or the Dario-Landau instability that does not permit flame to be very flat. And so we are going to see that. Another comment that I must make is that when when u is negative, clearly there is no solution. The square root become imaginary and there is no solution. But you don't expect that you can sustain a flame when the velocity is below the adiabatic flame temperature. Of course, what happens if you provide the flow, which you can control at any velocity that you like, is just that you're not going to get a steady flame, and sometimes you're going to get what we call flashback, where the flame try to get into the burner at some locations, okay? But those are other effects that, of course, not within this discussion. I'm putting back this figure that I showed you before, that to show you the streamline that are exactly the same way as we described them. You have almost a uniform flow coming from the burner, and then the streamline are deflected towards the normal surface to the flame. Okay. Another interesting thing that you could do is actually to use Bernoulli's equation along a streamline to describe, let's say, the gas velocity on the burn side. So if you want to use Bernoulli's equation, well, along this part of the streamline, from this blue point to this blue point, well, you can use Bernoulli's equation because it's an inviscid flow, and so you can relate immediately the pressure and the velocity at these 2 points. Well, the next thing you have to do, moving from 1 to 2, you have to use the jump relation, right, across the flame surface. And after you go from 2 to, let's say, any point that you like along the streamline, again, you can use the Bernoulli's equation, but of course with a different density, with the burn density. If you do so, you can obtain, for example, an expression for the velocity far downstream. And what you will see is that it depends on the tangential velocity, V2, at the flame. You know, I don't want to discuss that further because of lack of time. But what I want to say is that, in general, the incoming flow being uniform will remain uniform up to the flame. The reason for this is that since viscosity is negligible, a uniform flow is an irrotational flow. And in fluid mechanics, we know that an irrotational flow remains irrotational unless there is dissipation or other effect that would cause the introduction or the vorticity introduction or vorticity creation. So here there isn't, and so the flow is potential and remain potential up to the flame. But behind the flame is no longer potential because there is vorticity created at the flame. So the flow in the burn gas, it's a rotational flow with vorticity created at the flame, and it's more complicated to solve. Okay? And so in general, if you want to solve the flow field in the burn gas, it will have to be done numerically. I don't know of any other discussion in the literature of that, of this except numerical result. Now, what is interesting is that one can, in fact, obtain expression for the vorticity generated at the flame. And that you will see in this next discussion. What I'm skipping here is just a small detail that if you would like to find the flame shape and the incoming flow from the burner is not uniform, but a Poiseuille flow, you can do it at the expense of a little more complicated mathematics, but nothing more than that. There is one thing that is interesting, is that the extent of the flame is a little bit shorter than the entire flow field. And the reason for this is that, remember that the normal component to the flame surface must be equal to the laminar flame speed. And where the flame very near the wall is very small, clearly it cannot have a component equal to the laminar flame speed. And so the flame will stop at these 2 points here, and that you can obtain from this inequality. Okay? So this is a maybe a detail here I will skip. So the vorticity production at the flame, I will go through this also very quickly. And I did that for a steady two-dimensional flame because it's simple enough in that case to show what it is. So if you start with the Euler equation for steady flow, it's not very difficult to write the Euler equation in components which are normal and tangential to the flame. And if you do that, and you integrate them appropriately, you obtain that the change in vorticity from one side to another is given by this expression. So rho 1 and rho 2 is the density on side 1 and side 2, and the same thing with Vn1 is the normal velocity on side 1. And W2 and W1 is the vorticity on both sides. And this is the time, this is the derivative along the surface. So those are the gradient, if you like, of the tangential velocity square, okay? Now, if you think of this as a flame sheet, and 1 is the unburned gas, Vn1 is known. Because it's steady, that's the laminar flame speed. And so everything here is known, because this is rho unburned, rho burned, and so on. And so you can write that the vorticity jump across the flame is, in fact, this expression. Sigma here is the thermal expansion, which is the density ratio. And it depends on whether there are gradient of the tangential velocity along the surface of the flame. And so one often can use this relation together with the Rankine-Hugoniot relation as is convenient to obtain a solution. It's not more information than what you have here, but it's equivalent, but in a different way, and sometimes it's useful. But my main point was to make sure that you see or you understand that across the flame there is vorticity production, not across a planar flame, but across a curved flame in general, there is vorticity production, and that you can compute that vorticity production, okay? The comment that I made here, it's a quick one, saying that a Bunsen flame is another experimental way to determine the laminar flame speed, because we can measure the angle of the cone, theta, and since we know the incoming velocity u, we can calculate, or as a consequence, we can obtain what the laminar flame speed is. Okay, here is another example of again, a flame which is not flat, and that's a spherically expanding flame. So what we have is a mixture that is ignited at the center at some point, and because of the symmetry, the flame will remain a sphere and expand out, okay? And that can be done, as you see here is an experimental observation of a spherical flame. Note that the radius is quite large in this case, and it justified the use of the hydrodynamic model, because the flame being a fraction of a millimeter, or a millimeter, let's say, is small compared to 2 or 3 centimeters, okay? So the delta parameter that I have used before now is the flame thickness divided by the radius. So when the radius is small, clearly the description is not good. But when the flame have reached a certain size of a centimeter or so, then that's a good description. Okay. So now we can write the continuity equation, the momentum equation, the jump relation across the sphere, and we can solve the problem quite easily. Note that the continuity equation requires that r square rho v is a constant, and so inside the pocket in the pocket of the burned gas, which is inside the flame, the velocity goes like 1 over r square is not possible, because otherwise it become infinite at the center, and so the velocity must be 0. So this the burned gas that are enclosed by the flame remain, in fact, stationary, remain at 0 velocity as the flame expand out. And when the flame expand out, it set up a velocity in the gas. First of all, there is a sharp change across the flame, of course, and then the velocity will decrease according to this relation, decrease like 1 over r square, and goes to 0 at large distances from the flame. The temperature is described by the curve, by the green curve here. It's the adiabatic temperature, and then it dropped to the unburned temperature Tu. And out of this description, one obtained the propagation speed. Propagation speed is, in this case, r dot is the velocity of the interface of the sphere relative to a fixed coordinate system. And you obtain that r dot is equal to sigma SL. It comes from exactly the equation for the flame speed, which I which is written here, namely the propagation speed relative to the unburned gas, V at R plus, has to be equal to laminar flame speed. When you evaluate this from this relation, you obtain the propagation speed to be sigma times SL. So the propagation speed is the density ratio multiplied by the laminar flame speed. Okay? And remember that this is at large distances, and so it's only when the flame reaches sufficiently large distance you expect that the propagation speed R dot represent derivative with respect to time, if you didn't catch that until now. It's equal to sigma SL. In other words, it goes to a constant. And those are experimental observation of propane-air mixture at different equivalence ratio plotted as a function of the radius. Remember that the radius is the same thing as time because if you differentiate this relation, it tells you that the radius is sigma SLT. Of course, that is, well, so time and the radius are proportional to each other. And so what you see here is that when the flame radius is small, the propagation speed is not that yet, but it will reach eventually this asymptote at larger, when it becomes large enough. What is interesting in this figure, by the way, is that for some mixture, the propagation speed increase towards the asymptote, and for some other mixture like this or this, it decreases towards the asymptote. And later on, I will show you why that is the case. So this theory at the moment does not give you that information, doesn't tell you, it just gives you just the asymptote. So, and just so that you remember that the difference between these is the equivalence ratio. So it's, let's see, these are the where is it? The triangle is here, and those are the squares are here, isn't it? So the lean flame behave like this, the rich flame become like that. But the distinction is not exactly stoichiometry, in fact, okay? In other words, what distinguishes one behavior from another is not exactly stoichiometry. So we're going to discuss that a little later. Again, that's another way to measure laminar flame speed. Essentially, it's based on this graph, on this measurement. If you let the flame propagate to sufficiently large radii, then the propagation speed is sigma SL. You take the propagation speed, divide by sigma, and you obtain the laminar flame speed. Well, it sounds very simple, very nice. There's two caveats here. The first one is that if the flame is too small, clearly that doesn't behave like this, and it's not an appropriate way to determine laminar flame speed. So you cannot take measurements when the flame is sufficiently small. That doesn't give you the answer. Well, then you say, okay, so we let it go and it become large enough, and then we measure. Well, that's very nice, but what happens is, as we shall see later, when the flame becomes large enough, it's subject to hydrodynamic instability, and so already it becomes cellular. It becomes cellular, you cannot measure it this way. So there is a range of conditions where that's appropriate and that's acceptable, and that is one of the, I mean, every method that I have mentioned has its pros and cons, and so. Okay. This is an important thing. So as the flame expands, clearly change its area, right? So you start with an area, the area is given by 4 pi r squared. And if you ask how does the area change in time, well, you differentiate this, so that becomes 2r r dot. And if you divide by A, in other words, you find the relative change in the surface area of the flame, you obtain it's 2r dot over r, okay? Well, that is known as the flame stretch. I'm showing you this in a simple case because we can determine the flame stretch very simply, which is defined, by the way, as the time rate of change of the area relative to the area. It obviously have units of 1/2, and you can obtain it in the case of a spherical flame from first principle. It's very, very simple. But if my flame is going to be a surface of that shape in general, I would like to know what the flame stretch is at every point along the surface, and we are going to see very soon how we can compute that or obtain that. So this is for the simple case, just to see it. And in particular, note that when R becomes very large, K go to 0. In other words, when the flame becomes very large, it flattens out, and a flat flame does not change its area if it's under a uniform flow, so it's not stretched, and so that's fine. Okay, the next example, I will almost skip the detail, just show you the end result, because it's really, it's a little bit too long. So it's flames in counterflow. And these are two configurations. There is a third one that I will mention in a minute. So you can have two burners that are exactly aligned to each other. If they are not aligned, the problem is that the flow is not exactly as described here. They must be aligned to each other and at, let's say, some distance from each other. And you can either provide combustible mixture, the same, say, mixture in both burners, or a mixture from one end and an inert gas from the other. Depending on which configuration, you will either obtain twin flames or a single flame. It's a single flame, which is because there is no combustible mixture here, clearly. Now, the twin flames are going to be, of course, symmetric only if you have the same mixture and everything is symmetric, clearly. Okay, now they are flat because that's what observations show us, that you can get flat flame in this configuration. And so we are going to try to describe this mathematically using the hydrodynamic model that we have discussed so far. An equivalent problem to this is if I put, instead of this symmetry line, a surface, right? So it's going to be a flame in a stagnation point flow. So there's a surface, so you impinge a gas into a flat surface, and it's an equivalent problem. And here is the burner, and the incoming gas is coming here, and here is the flame. So the first thing is that remember that as the gas is crossing the flame, we said that the streamline are deflected towards the normal. The normal is the axial direction, so it will be deflected towards the normal, so the blue curve will become green, right? Okay? So this is the deflection across the flame. Now, the flow, if there is no combustion, in other words, if it's an inert gas against the wall, then the axial velocity u as a function of x, I think I called it z above, is it? Z, yeah, will be simply a straight line, and it has, of course, to go to 0 at the wall where z equal to 0, right? However, because of the deflection of the streamline, the flow actually feels that there is a, it wants, in a way, to go to a different stagnation surface. But clearly, the wall cannot be displaced, so the flow gets displaced. So actually, the flow with the green line, it's equivalent to the flow of a non-combusting mixture, but against a stagnation point located away a distance a from the wall. So that's the reason why the incoming flow is not the standard potential flow, which is 2 epsilon z, but is 2 epsilon z minus a. Okay? And the distance a can be computed, or must be computed, as part of the solution. Okay, so this is the incoming flow, which is a potential flow, and it's known, with the exception of a. And then we have to solve in the burn region. And remember that the burn region, the flow is now rotational, so the potential flow solution is not good, so we have to solve for the rotational flow. Okay, so the first thing is we can write the jump relation across the flame, and I have used here the jump relation of the velocities and the vorticity. And the last relation is the flame speed relation that says that the velocity just ahead of the flame must be exactly the laminar flame speed. And so that's expressed here, which gives you a relation between the position of the flame and this unknown A, what we call the displacement, the flame displacement, the flow displacement A. Okay, so now we have enough equations, which are the Euler equation, and enough condition to solve the problem on the burn side. The solution is not very straightforward, but it essentially uses the vorticity equation and then the stream function vorticity formulation. And if you do that, you obtain that the solution for U is no longer a linear relation like I have told you here for the for an inert gas, but rather it depends on this functional dependence on Z, which is more quadratic. And I will just show you the form of the solution. Let's focus on this red curve, for example. It would be, this is the potential flow, the incoming potential flow. Then there is a jump across the flame. Sorry, the figure is a bit crooked. It meant to be vertical. And then and then the burned gas follow more a quadratic relation and must be go to 0 at 0. And here is a relation, or here is a comparison between which was done by these people, by the way, between the theoretical result, which is essentially the solid curve, and I will explain this in a minute, the solid curve and the data, the experimental data. I believe that one can probably present it in a more precise way. It's done roughly because what they have done, they have put the discontinuity at the unburned side, and it's more appropriate to put it on the burn side. But anyway, that's a detail. Generally speaking, you see it's the same trend, the same behavior. Now, the reason for this, it's because clearly what you have in the experiment, you don't have the flow coming from infinity and following this red straight line, but rather it's coming from the burner where the flow is uniform. So it starts uniform, and then as it gets closer to the wall or to the symmetry line, then it behaves more like the stagnation point flow with a constant slope or a constant strain rate. Okay, now here is something which is important. So suppose, remember that this I didn't say, but the configuration that I have been looking at here, it's an axisymmetric flow. So it's RZ, but also there's the angle theta, but it's axisymmetric, so there nothing depends on theta. However, the flame surface is going to be a disk, right? Okay, so if we move forward here, we see that the area of the flame at some point in time, let's say it's pi r square, which is this area, the purple area, right? Well, at a slightly different time, the area is going to be pi r plus delta r square, where delta r is a small change in the surface. And why there is a small change in the surface? Because there is a velocity component, which is the green component here, along the surface, and so the delta r is related to this v delta t, right? And so the area from the purple to the green changes, and as a result, if you compute dA by dt, you can evaluate it and then compute the stretch and obtain that it's exactly 2 epsilon. So it's exactly equal to the strain rate. So in other words, the flame now is stretched, not because you visually see an area change, it's just that because any elementary area is stretched by the flow, the tangential component of the flow. So we have seen 2 ways that a flame gets stretched. One, as it propagates out, the area change. The second one, when it's subject to a strain, it is stretched by the straining field. And we're going to see the more generalization of this. So, maybe I should quickly make this comment. Since the flame is stationary, then the flame speed, by definition, is just the velocity just ahead of the flame, namely at this position here, right? And so in principle, you can determine it experimentally. As we shall see later, in fact, because this flame is stretched, it's under strain, the flame speed is not exactly the velocity here, but the difference between this and the laminar flame speed is proportional to the stretch rate. Okay, that's something we'll discuss later. So if that's the case, then one can use this idea again to determine the laminar flame speed by taking data of experimental data of the flame speed, namely of the velocity just ahead of the flame, and graphing this as a function of the strain rate. And then you extrapolate to where the strain rate is 0, and you should get the laminar flame speed. Of course, this should be done close enough to, in other words, for small enough strain rate so that this extrapolation is valid. And in the literature, you can find situations where you have to be a little bit careful because it's not quite valid always. It can give you a slightly lower, slightly higher value, and there are some discussion from the theory that show why that is the case. Mainly, the main reason for this, it's because when you, this is a brief reason why, but that's exactly the reason. What happened here is that when you measure the flame speed at this position, it turned out that this position is not exactly the cold edge of the flame. In other words, it's already a little bit within the preheat zone, and as a result, there have been a little bit of thermal expansion effect at this point. And as a result of this, it gives you, it misses to give you the right value when you extrapolate to 0 stretch. Okay, so this, and there is a paper in the literature, if you're interested, I can refer to you that show that, that have that discussion. So this was another example of measuring flame speed. I wish I had time really to discuss this example on closed vessel in more detail, but I really don't. And so you have some detail in the lecture, so I will leave it there. The main point here is that because it's in a closed vessel, then the equations require also determining this capital P. Remember, we discussed that. And so that's part of what you need to determine the solution. And suppose that I skip some of these details and just show you the example I did, which is a one-dimensional flame, but so a planar flame propagating, but in a closed tube. Then you can actually determine the velocity field. You see the burn gas propagate away from the flame as they expand, but then they have to go to 0 at this point. And then the unburned gas, because the flame is moving and the gas has to be 0 again at that wall, it pushes the gas ahead. And so what you have is eventually is a velocity field as shown here, which is also shown here. So if you focus, say, on one of those lines, let's say the red one, so as when the flame is at this position, the gas ahead is moving along the axis in the positive direction, and it decreases to 0, and the burn gas is moving in the opposite direction, is slowing down and goes to 0. And if you calculate, and well, the expression also gives you an expression for the pressure buildup, and that is seen in here. And what you see is that the overall pressure in the tube increased by almost 8, by a factor of 8, which is quite significant, okay, in time. And finally, one of the probably most interesting thing is this graph, is that you see this is the flame temperature, this is the unburned gas. So first of all, the unburned gas doesn't stay at the cold temperature, but it increases slightly. Why? Because there is compression. There is adiabatic compression. And what happened in the burn gas doesn't stay at the flame temperature. at the adiabatic temperatures also increases, again because of adiabatic compression. And so you see the highest temperature in the field is actually at the burn side of the flame. And there are experiments that have done this in a spherical bomb, and they show that the point where that shine the most, that is illuminated the most, or the highest temperature is at the center of this bomb, which is equivalent here at the burn side. I think it has a name, but it's not very common in the literature. And it's similar to Mach, but I'm not sure what's the right pronunciation because unlike Mach number, it has an E at the end. So it's a Mach effect, but it's not the same Mach as the Mach of Mach number. Okay, so let me see. We still have a minute or two before we break. And so this is still in one lecture that really I had too many slides in it, but this is quite important to skip. And so I want to at least spend 15 more minutes in the next lecture to cover this. So now this is the hydrodynamic theory revisited. I said that at some point we only took the leading order solution, and we saw that the leading order flame speed is a constant, and we can apply the Rankine-Hugoniot across the flame surface. But within the same assumption, in other words, a thin flame, one can carry out the analysis to a higher order, to order delta. In other words, include also order delta effect. And order delta means effects which are due to flame thickness. And so those are important effects in many situations because within the flame there are diffusion effects, and when these effects are not in balance, they can cause influences on the overall flame position, speed, and so on. And so it's important to include these effects which are of the flame thickness, of the order of the flame thickness. And so when you do the analysis, you find out that instead of obtaining exactly the Rankine-Hugoniot relation, you have contribution, non-zero contribution on the right-hand side. So the first question you ask, well, what does it mean? The Rankine-Hugoniot say that the first relation says the mass flux in is equal to the mass flux out. So what does the right-hand side mean? Well, it means that whatever is going in, there may be accumulation inside the flame, or there may be transverse gradient from the side, okay, from the side. Remember that the flame now is not a true surface, but it has some thickness, order delta. And so these effects are not negligible, and so they must be accounted for, and they are accounted here. The second thing you obtain is that the flame speed, namely the propagation speed relative to the incoming gas, is not a constant like was assumed, say, at the time by Dario and Landau, but it is the laminar flame speed corrected by a factor which is, in fact, exactly the flame stretch that was derived, as I said, and the coefficient in front of this relation is known as the Markstein length. The reason it's called the Markstein length, it's because in the 50, Markstein have hypothesized that, well, the laminar flame speed, the fact that the flame speed is equal to laminar flame speed is not quite accurate. And so he said, well, let's assume that there is a coefficient that is proportional to curvature. So Markstein introduced the influence of curvature on the flame speed, and the coefficient in front has since been called the Markstein length. The difference between the hypothesis of Markstein and this theory is that we know exactly from the derivation what is the Markstein length. In other words, we have an expression for it, and that's what I will discuss soon. And so we have two things to discuss here. One is flame stretch, the other one is the Markstein length. Flame stretch has units, as I said earlier, 1/2, and Markstein lengths have units of lengths, so it's centimeters, so obviously this is compatible, or it has the same units as it should for a flame speed. Okay, so let's take a break and then we come back.